Why bother with all of the complicated notation associated with limits? Why don't we just use our normal English language to describe something approaching something else? I'm going to show you why, and this is sort of a preview of the calculus. You know that when something bounces off something else, like it could be a billiard ball or it could be light reflecting off a surface, if it's flat, the incoming angle equals the outgoing angle, and that lets you predict how something will bounce or how light will reflect. This basic idea is at the base of a whole lot of stuff. If you need to work in acoustics, if you need to work in optics, if you need to work in mechanics, like calculating trajectories of things, this is like a really basic fundamental kind of physical principle. Okay, but most things in the world are not flat. Most things in the world are curvy. So what happens if, for example, light reflects off a curved surface? Well, I think it's pretty intuitive that there exists a line, a tangent line here, where then you can say that the incoming angle with respect to that tangent line should equal the outgoing angle, and that's the answer. But what is this tangent line exactly? I have an intuition about it. Let's zoom in here and I'll show you what my intuition is. So if I have a curved surface, I imagine a line, I can draw a bunch of lines that touch only this point. So here's a line that touches only that point. Here's another line that touches only the point. Here's another line that touches only the point. And algebraically, you could write a whole bunch of equations with different slopes that all just touch one point. But only one of them feels balanced, quote unquote. So what does it really mean to be kind of balanced? To me, the tangent line is one where, I want to say this angle equals that angle, but that doesn't really answer anything because how do you measure the angle between a straight line and something that's curving? So again, this is just me kind of groping to try and express my feeling about what would make this tangent line balanced on one side or the other. So this is why we need limits. We have this feeling about what this kind of balanced tangent line should be. But if I asked you to rigorously calculate, I give you an equation, y equals x squared, and I tell you that I want you to calculate what's the tangent line at a particular point and to tell me what the slope is, you'd have no way of calculating that because it's all very fuzzy. It's all very intuitive. So one of the big insights in calculus is that you can define a lot of things as the outcome of a limiting process. You can define a process that's getting closer and closer and closer to the thing that you want, and then use limits to actually define the thing that you want. So what would that look like? So what I want to be able to describe this perfectly balanced tangent line. And the way that I'm going to define it is I'm going to start by defining, I'm going to start at a point A. This is point A, the place I want to find the line tangent at. I'm going to make a point B that's some distance away from A. So if I start at 2 and I add 8, I get to 10, and there's B. So I can connect those with a line. Obviously, this line is not a tangent line at A, but what I can do is I can make this line get closer and closer to what I think the tangent line should be by making this distance smaller and smaller. So if I move B along the curve closer and closer to A, here when B is only a distance of 3 away from A, it's moved down the curve and the line looks a little bit closer to the tangent line. If I keep moving it, now it's at 2 and 2.1, so that's only a distance of 0.1 away from A. And so these points are almost on top of each other, and the line connecting the two is very, very close to the tangent line at A. And so you can see that if I wanted to get even closer to the tangent line, I could continue this process and make them even closer. So you could say that the tangent line that I want, this is still quite informal, and we're going to do this algebraically in a second, but we're saying the tangent line we want, we can think about it as being the limit of the line that connects A and B as this distance between them gets smaller and smaller. So as this distance d approaches 0. And that will give us a precise algebraic way of actually calculating, what is the equation for this line? What would the number for the slope be? It might be easier to visualize using Desmos. All right, so here is y equals x squared, and I put a point A right here at 2. Let's get a point B that's some distance away. All right, so here I've got my point B, and you can see that I can make it get closer and closer to A. Now let's construct a line that goes between them. So here's a line between A and B. Now, as I move B closer to A, you see that when B is directly on top of A, well, when it's directly on top of A, we don't have any point, but when it's very, very close to A, this looks like the balanced tangent line that we want here. So that's the idea. We've defined the mathematical thing we care about as the result of a limiting process, as the end result of this kind of infinitely getting closer and closer to something. So let's do it algebraically. And this is something that you're going to be doing in the problem set, but I just want to illustrate how it works. Let's, instead of finding the line straight off, let's just choose one of the facts about a line. So when you think about a line, you think about a slope and a y-intercept. And it seems like slope is going to be a relatively easy thing to calculate here. Because if I want to know the slope of the line from A to B, I know I just have to figure out, like, what's this difference in heights, the difference in the y-coordinates, divided by the difference in the x-coordinates. Okay, so here's the plan. Step one is let's find the coordinates of A. So I started by saying I want to find the tangent line at a particular value. So 2 is just the choice I made for where do I want to make the tangent line. So that's 2. And then I know that this is the curve y equals x squared, so I also know that the y value should be 4. All right, so that's A. What about B? So instead of trying to decide some number that we want to move over by, so if it was 8, this would be 10. Instead, we want to be taking the limit as this distance gets smaller and smaller. So this needs to be a variable. So let's call it d for distance. So in that case, what's the coordinate here? Well, if I start at 2 and I move over by d, the answer must be 2 plus d. Okay, so that's the x-coordinate of b. What's the y-coordinate for b? Well, remember, this is just the curve x squared, so I'll just take my x-coordinate and I'll plug it in, and that's the y-coordinate. So the y-coordinate is 2 plus d squared. And if I chose a specific value for d, I could plug it in, and these would give me actual numbers. So for example, if I chose 8 here, then this coordinate would be 2 plus 8 is 10. And then if I squared it, I would get 2 plus 8 is 10. Squared would be 100, and that would make sense. All right, great. So now, what's slope? I know slope is change in y over change in x, where this is change in y, and this is change in x. So let's go ahead and write expressions for that now. Let's see, change in x looks like it's exactly what we just called d. So change in x, is just d. What about change in y? Change in y is the difference between these two y-coordinates. So it must be 2 plus d squared minus 4. And let's see, where did we get 4? We got 4 because it's the square of 2, because we took 2 and we plugged it into the function. So this is actually 2 squared. And the only reason I'm doing that is sometimes it's helpful to see the pattern for where we got a value from. All right, so now I have this general expression for what is the slope, but it's all in terms of d. So now if I make d smaller and smaller, I can plug in a number for d here and figure out what's the slope. So something I wanted to point out, here I've written the expression for change in x, and here's the expression for change in y. It's exactly what we just wrote on the whiteboard. So you got to imagine the triangle here. Imagine change in x is the horizontal distance between A and B. Change in y is the vertical distance. So as the distance gets smaller, each of these numbers is getting closer to 0, which makes sense because the horizontal distance is going to 0 and the vertical distance is going to 0. So when they're almost on top of each other, you see horizontal distance very small, vertical distance very small, and we can keep making it smaller and smaller until there's 0. So each of those is approaching 0, but remember slope is the ratio of those two. So S is what I'm going to write for slope. Slope is change in y divided by change in x. So now watch what happens to the slope. here, as my distance is getting smaller, delta x is going to 0, delta y is going to 0, but the slope is getting closer and closer to a number 4. Here, let's make this actually, let's do this. Let's make the step even smaller. So you can see that when d is very small, the ratio of the two is approaching a fixed number. So that's what's magic about limits. We have this fraction where the numerator is getting closer and closer to 0. The denominator is getting closer and closer to 0. But when you divide them, the overall fraction is getting closer and closer to 4, which is the slope that we want for this tangent line. So let's calculate this out the rest of the way. I just defined the slope from a to b as this expression, and now I want to know what is that slope as b gets closer to a, as this distance approaches 0. So let's write it. I'm going to write slope equals limit as d approaches 0 of this expression of 2 plus d squared minus 4 divided by d. All right, so how do you figure out what this limit is? If I just plug in 0 for d, I'll get, let's see, I'll get 2 plus 0 is 2 squared, so that's 4 minus 4 is 0 in the numerator. And d, if I plug it into the denominator, that's also 0. So I get 0 over 0, which is undefined. So that's why we need a limit. If I look at this function, it's got a hole at d equals 0. But I don't care what happens at 0. Because you can't have a line when a and b are literally on the exact same point. I want to know what's the slope getting closer to as these two things are almost on top of each other. So we can algebraically simplify. Let's expand the numerator here as 4 plus 4d plus d squared minus 4. And this is still inside our limit. So now I've got 4 minus 4. So those add to be 0. I've got a d in both terms here, so that means I can now factor out a d. So I've got d times 4 plus d, and then that's all over d. And now d divides d. So now I've just got what's the limit as d approaches 0 of 4 plus d. And here, I've got no problem plugging in the value d equals 0. When I do that, I get just 4 plus 0 is 4. So now I have a value, whoops, you can't see my little smiley face. There we go. So now I've figured out that this is what the slope must be. And that's what we saw in Desmos as we were actually making that distance close to 0, as we were seeing that this ratio of change in y over change in x was getting closer to 4, and now we've algebraically verified that actually, yes, it is 4. So if I actually wanted to write the equation for this tangent line, I know the slope is 4, but like what's everything else? Well, you can just use the form of the line that's y is slope times x minus a particular x value plus a particular y value. So let's go ahead and evaluate that using the point here at a that we know. I just calculated that the slope is 4. I know that the coordinates of a are 2 and 4. So now let's actually graph everything on Desmos and see what there is to see. So here's the same graph that we've been looking at. Let's get b further away here. B is going to go over here now. So I'm just going to enter the equation that we just calculated. So it was 4 times x minus 2 plus 4. And I've lost track of all my lines. So let's make, so you see that as b, So as b gets closer and closer to a, you see that the black line is getting closer and closer to this tangent line that we calculated in purple. So bringing it full circle, to answer the question why limits, we started with this idea that a tangent line is important because you have to figure out, or like often it's useful to figure out how something will bounce off of something else. And if it's bouncing off a curved thing, You need to know the tangent line because that's what's telling you which angles have to be equal. And we had this intuition that the tangent line was sort of like balanced. It wasn't sloping too far this way or too far that way. But we didn't have any idea how to calculate the number because it was just this feeling that we had. So what we did was we described something that wasn't a tangent line, but then we described a process where we could make our thing closer and closer and closer to the tangent line we wanted it to be. And that's why limits are useful. Instead of trying to describe what you want directly, you describe a process that leads towards what you want, and limits will let you algebraically describe that process, and then you can evaluate what is the goal that this process is getting closer and closer to. That's it. Come back in the next video for a bunch of kind of ho-hum nuts and bolts tricks for doing this kind of algebra. But this idea about conceptually why do you want limits, that's the powerful idea at the heart of calculus.